So now we've established the theoretical framework for equilibrium constants and calculating what will happen with reactions. Let's go through some practical examples now. First, we'll look at how you calculate an equilibrium constant. Well, we mentioned that what we need to calculate is the standard Gibbs energy for the reaction, and then use the equation that this is equal to minus RT natural log of Kp to find our equilibrium constant. So let's look at an example of doing that for the decomposition of ammonia. So ammonia gas can decompose via this reaction into H2 gas and nitrogen. And we'd like to find out, what is the equilibrium constant at room temperature. So to be able to do this, we need to know what is the standard Gibbs energy for this reaction. Well, what we need is, one thing you may notice for this reaction in particular is this is the reverse of the formation reaction for NH3, for the, like the Gibbs free energy of formation. So if we look up the value of delta G naught for NH3, it is equal to negative 16.367 kilojoules per mole. So that means for this reaction, it's the reverse of that, because this is the opposite of the formation reaction. The other way we can look at this is that the values for delta GF for our two products are equal to 0, since they're both elements. So we can say, okay, delta G naught for the reaction is positive 16.367 kilojoules per mole. Okay. So then we can go ahead and rewrite this, say that, okay, natural log of Kp, using this equation up here, is equal to minus delta GR naught divided by RT. And then we can go ahead and plug in the values we have. So natural log of Kp is equal to negative 16.367. Now we've got to be careful with our units here. So I'm going to go ahead and express this in terms of joules instead of kilojoules. So when you put times 10 to the third joules per mole, that's our delta G value, our standard delta G value, divided by 8.3145 joules per mole times Kelvin. And then we need our temperature, which is 298 Kelvin. Okay, and if we go ahead and plug in all of those values, natural log of Kp is equal to minus 6.602. So then if we take the exponential of that, Kp will be equal to e to the minus 6.602, which ends up being 1.36 times 10 to the minus 3. Okay, so that is a pretty simple, straightforward example of if you know a reaction and you can look up the standard Gibbs energies of formation for that reaction in a table. This value came from a table in your textbook. You can then calculate what's the equilibrium constant. And what this tells us is, if you remember back to your freshman chemistry class, an equilibrium constant less than 1 means that we're favoring the reactants. So at standard conditions, to be clear, this is at standard conditions, the equilibrium will be shifted mostly to the left. We'll have more ammonia than we will hydrogen and nitrogen, which makes sense. Ammonia is a pretty stable compound. You can buy it in bottles or whatever, and it doesn't just spontaneously decompose. Or, well, it does, just not very much. So this is a straightforward example of how we can calculate an equilibrium constant from standard Gibbs energies of formation.